Hi, my name's Eric, and we're going to do another video on a topic that's found commonly in a first-year algebra class. The name of the topic is solving or finding solutions to linear inequalities in two variables. Okay, first of all, what's an inequality? It's any statement in math that contains one of these five symbols. These symbols are read: is not equal to, is less than or equal to, is greater than or equal to. So if you are asked to solve an inequality that has, it's going to have one of those symbols in it. And if it's got also two variables, like an x and a y, then this video may help you figure out how to solve. So let's take an example of this. Y is less than or equal to half x plus 4. First of all, the solutions don't look like solitary numbers. You can't say the answer is 8, because there are two things that have to be answered here. I need an x and a y. Now, if you say the answer is 8 for x, and the answer is 3 for y, so 8 and 3, like this, you may be right, you may be wrong, but at least now we can talk about it. We can go test out to see if this is a solution. Is it a solution? Is it the solution, right? Because there's a difference. Sometimes there's only one solution, and sometimes there's two or three, or a lot more than we can count or write down. So all these things will come up today in this video. First of all, let's decide whether or not this is a solution, okay? If x is 8 and y is 3, I can plug these in, and that would look like this. All right? Half of 8 is 4. 4 plus 3 is 7. Now we can decide whether or not this inequality is true. Is it true that 3 is less than 7, or that 3 is equal to 7? Yeah, 3 is less than 7. Because this came out true, you can go back and you can say 8-3 is either the solution or at least one of the solutions. Now, which is the case? Oh, geez, there's a lot of solutions. You could stand up here for the next hour and a half and not make an exhaustive and complete list of what the solutions look like. Let's look at another solution, just so that you know I'm not lying to you. I mean, there's scads of these things out here. Here's another possible solution. Let's see. If I go with x equals 10, and if I go with y equals 7, that's going to be a solution. Okay, how do we know that? Again, plug them in. So you put 7 here, and you put half times 10 plus 4. Half times 10, or half of 10, is 5. 5 plus 4 is 9. 7 is less than or equal to 9. Yeah, that's true, and so 10, 7 is a solution. Now, because there are so many solutions that you could not possibly write them all down on a page, you can't make a list of them, we have a different method of finding the solutions. Basically, all the solutions to this inequality can get graphed. And when you do that, you find out that there's a pattern. That all the solutions end up sort of being found or congregating in one area. All the non-solutions, things that don't work, are found somewhere else. And in between the area of solutions and non-solutions is a border or a boundary. And in the case of linear inequalities, that boundary is a line. And so what we're going to do is quickly treat this as if we're just graphing a line. I've got a previous video that I think does a pretty good job of explaining how to graph a line. And this line compares to the slope-intercept equation. I know this says less than or equal to, and that's different, but you can still go about this just the way we did in the other video. Okay, you can start with this. an ordered pair that uses that 4 for y and uses 0 for x. It's called the y-intercept, and it's found on the y line right here. And then you can analyze this fraction, which is called slope. And remember that the number on the bottom means go to the right and should always, always, always be positive. The number on the top means go up when it's positive and down when it's negative. But this time we have positive, so we're going to go up. So we go 2 right, 1 up, 2 right, 1 up, starting from the y-intercept. If we run out of real estate, we go 2 left, 1 down, like this. Okay, the line that goes through these points divides the solutions from the non-solutions. A minute ago, we had a solution of, what was it, 8-3 or something like that. That's found down here. A non-solution for this problem is going to be found up here. And to test that idea, let's pick a point that is 2 units to the left and 4 units up. And I'm going to show you that this point, -2, 4, I'm going to show you that that's a non-solution. And then I think I'll pick another point like this one and show you that this point is a solution. So first the non-solution. -2, 4. We plug into here like this. Half times -2 is -1. -1 plus 4 is 3. It is not true that 4 is less than or equal to 3. It's actually greater than 3. So because I plugged in these points and I got a false statement here, that's not a solution. That one right there. And it turns out anything that you plug in above this line is a non-solution. Whereas anything that you plug in down here, below here, is a solution. And I've done enough of that I don't feel the need to do anymore. The last thing though that I want to do for you is show you a quick guide to drawing the solutions, okay? Because there's really only about 4 possibilities. You can have a problem that looks like this. You can have a problem that looks like this. You can have a linear inequality that looks like this. Or you can have one that looks like this. What I'm going to show you is basically a guide to doing 2 things. Number 1, how should you draw the boundary line? And number 2, how should you shade? In a problem like this, where it's a strict inequality and it says greater than, so y is greater than, you're going to have a broken boundary line and you're going to shade up. Because the solutions will be above your line. This is very similar, but it includes an equal sign, and that basically says you don't need a broken boundary line, you need a solid boundary line, because the numbers that are on the boundary line are good. I will say a few more words about that. So this is style A, style B, style C, and style D. Style C says y is less than, and it's strictly less than. You will draw a broken boundary line and shade down. And the last style, less than or equal, y is less than or equal to, has a solid boundary and it shades down. Okay, you'll notice that the problem that I was working on up here, if you compare this to my chart, you see that it compares perfectly with D. D tells you 2 things. 1, make the boundary line solid. This. No dashing, no interruptions, don't make it broken. And then you should shade down, because the answers, as I have previously discussed, are found below the line. There are different ways to do this, but an acceptable and fairly quick way is just to kind of draw some stripes like this, and then we're done. If the whole thing about, you know, dashed or broken versus solid doesn't make sense to you, let me just do this. Pick a point that's actually on the boundary. Here's one. It is 2, 5. Okay? I'll highlight it in green. The reason I drew a solid boundary line is because 2, 5 is one of the solutions. And we can demonstrate that right here. You put 5 in for y, and 2 in for x. And I'll just do this quickly in my head. Half of 2 is 1, and 1 plus 4 is 5. This all computes to 5. It's not true that 5 is less than 5, but it is true that 5 is less than or equal to 5. And that's why this is a solution. And every point on this line is a solution. Okay, one more example. And this time we will draw a broken or interrupted boundary line. And we're going to do it, and you can tell that in advance, because this last example looks like this. It says greater than, strictly greater than. Okay, I already know that I'm going to have a dashed or broken boundary border, and I already know I'm going to shade above because the solutions are going to be above. Now, without putting too much emphasis on this, because I've done videos on this already, don't forget your y-intercept is found here, and it gives you a place to start. Don't forget that the slope should contain 2 numbers. And the bottom number is always positive, and it always means right. And this time, the top number, just like last time, means up. I could change that for you. Tell you what, let's do this. Let's put a negative there, and we'll change this to down. But that's not going to make any difference on the fact that I'll have a dashed boundary line, and that I will shade above it. Okay, I started here. This says 3 right and 2 down. 3 right and 2 down. You can also go 3 left and 2 up. Now, points along this line are not solutions. The solutions are above the line, like this. And I can demonstrate that. But I'd rather demonstrate that something on this borderline is not a solution. And I think that to demonstrate that, I will go with this point right here. This is 3, -1, okay? I'm going to plug those in and show you that they don't solve that inequality. I'll do that right over here. And I'm supposed to put the -1 here, and put the 3 here. I'm not going to get into a lot of detail on this, but you probably have a calculator that can do this for you. Essentially, I just cancel those 3's. What's -2 plus 1? Why, that's -1. True or false? -1 is greater than -1. It's not. If I had a little bar on here, well, they are equal, and then I'd say, oh, okay, that's a solution. But in the absence of an equal bar here, you can't say -1 is greater than -1, and so that's not a solution. Well, it's true for everything along this boundary. They're not solutions. And that is what the significance of an interrupted or broken boundary is. It says, you know what, you actually have to get on the other side of the line before you are in the solutions. I hope that helped. My name is Eric. Again, the name of the topic is graphing linear equalities, or solving linear inequalities in 2 variables.